Please, don't just look.
As I said, it must be a hell of a poster session. The largest we had, I think.
So I think we have to start.
Well, we can wait another.
Okay.
Let's wait a few minutes so that people.
Can you repeat yourself?
I can. Well, I'm not so good at PowerPoint. Well, maybe it is
Do you have
PowerPoint
a
karaoke
song,
because
maybe,
you end up
So
presenting.
RD50 song?
We should think about a hymn. Yeah, no, we don't. We have a logo which you can see on some of the slides, but
Let's describe the Schwarzwald.
indeed it is that's the view from called a place called Kanonenplatz, a bit high up on the city with our minster, and look into the wine mountains known Kaiserstuhl, the Emperor's Chair, and beyond
it's
that,
not a Schwarzwald.
on a clear day, you would actually know the Schwarzwald is at the
Yeah,
back
on
of
the
this
back,
photo,
yeah.
and here you would just about see France on a clear day.
Rhine River being just behind Kaiserstuhl, right?
Yes, yes.
So you should have picked an angle where we can see Strasbourg as well.
Maybe next time I can, if I knew I had a few minutes, I would take some panoramic city
yes,
pictures
yes.
and give you a guide. You can ask Claudia, she's been there a few months ago. November, yeah.
Okay, probably.
Yep. So we will resume the solid state detector session with 5 talks. The first one being on RD50 results presented by Uli Partzefal from Freiburg. And please.
Thank you very much. As I said already, must be a hell of a coffee break and a poster session with so few people here. But just shows the excellent place that we are in. So let's start. What is RD50? I suppose in a solid-state detector session, many of you know that. We are a CERN-based collaboration with more than 400 members. And the nice thing is that it collects all the LHC experiments and all the other small experiments. So we work across all the experimental boundaries. And the mandate we have is to develop radiation-hard semiconductor devices for very high luminosity colliders. Now, in the original interpretation, this would have been to develop for the phase 2 upgrade of the LHC, and the talks we have had early in this morning by Laura and by Alessandro give you clear evidence that this has been reached. Yeah, both constructions for the trackers here in Atlas and CMS and also the others have started. And the new mandate of RD50 is to go beyond the LHC, which for me mostly means FCC, where you have to reach radiation doses of a few 5 times 10 to the 17 neutron equivalent. And I'll show some highlights of the results, but first let me show you what kind of collaboration we are. So this is a worldwide collaboration, but if you look at the institutes, this is mostly European-based, what you can expect for a CERN collaboration, and then we have American, Middle Eastern, and also Asian institutes in there. I should also maybe add at this point, it is an open collaboration, so anyone with interest in semiconductor detectors can take part in RD50 meetings, and our slides are always public. You don't have to be an RD50 member to attend RD50 meetings. The structure is like this. Gianluigi and Michael are our spokespeople, and we have 4 pillars that we work on. Defects in material characterization, detector characterization, the new structures, which is where, for example, 3D detectors and LGATs are housed, and then full detector systems. And I have picked a few examples from all of these, because in these 15 minutes I can only show you a few highlights that are indicated here, where I'll just have a biased selection. And in terms of bias, I should disclaim I come from Atlas myself, so there's maybe a little bit of Atlas bias in these results. Let's start with defect characterization. So what happens if you have some hadron hitting silicon, a lattice, at a lattice site, you actually kick out the silicon, you create a vacancy and interstitial, and you get a very large range of point defects that can happen when you have enough energy. And then these defects can react. For example, a vacancy and an oxygen can form a cluster, vacancy and phosphorus can form a cluster, which would then deactivate your dopant. And the same can happen in slightly more complex ways when you have interstitials and carbon reacting. So the carbon at a lattice site could then become an interstitial, and then in the end you get a carbon-oxygen cluster, something very similar can happen for boron. And in these cases, you can see that the dopants that you originally had, they get deactivated, and this will have an impact on your detector performance, which in almost all cases is something undesired. I should also point out that these defects are mobile with a very strong temperature dependence. So if you actually have your detector, the warmer you have your detector, the more these defects move around, and this is something we call annealing. And that can, and you'll see later some examples of this, that can be used to improve your detector performance. Then more on defects. The main goal of the defect studies is that we want to identify the defects that are responsible for performance of the detector, and for example, look at the effective doping concentration, the leakage current, and the full depletion voltage, which is directly linked to the doping concentration. And you can see how different effects with their position in the band gap affect the macroscopic properties that we measure in a different way. So for example, the leakage current mostly comes from mid-band gap defects. And then if you look at the change of the depletion voltage, which is in fact coming from the change of the effective doping concentration, you see this is caused by defects which are very close to the band edges. And then another group of defects that in particular for the very high radiation doses is a limiter, is trapping. So you have states that can trap a charge that you have a signal charge in your detector and keep it for a while before releasing it, and which will reduce the signal available, so you have lower charge collection efficiency, lower signal in the detector, and in the end then just low detector performance. Tools we use for this, just one example here, is for example thermally stimulated current or TSC measurements, where you can then identify individual effects, like here a vacancy oxygen cluster, and then the aim is to exploit that information to reduce unwanted defects. Then one example here from the LHCb experiment from the locator is where an RD50 model, normally known as Hamburg model, which describes the evolution of the doping concentration and the leakage current, is used by the experiments to improve their detector performance. So LHCb, as most of you will know, has a vertex detector which is at present one of the closest to the interaction point. And you can see on this plot here, or actually maybe it's too small to see from the back, the various rings of the detector. And you see that the innermost here in this plot receive the highest radiation dose, and they have the highest depletion voltage measured. And when RD50 performed this scan a few years ago, they realized with more radiation coming in, they are reaching depletion voltages which they're not comfortable with running anymore. And then, based on this RD50 Hamburg model, RD50 decided to warm up the detector in a targeted way to accelerate the annealing, the beneficial annealing, so that they could reduce the effective doping concentration and also the depletion voltage. So you see these two lines here. This is what you would have had with no annealing. You notice that there's more radiation collected now in September 2018. You are still comfortable running with this targeted annealing step. You can also, well, I'll do that later. That you can maybe, if you know it, look a bit here and see that there is this type inversion happening at a low radiation dose. Then another way, slightly more complicated plot here, is how full depletion voltage and current looks in particular here in Atlas what I've chosen. So both large trackers, they continuously monitor the full depletion voltage and the current in their trackers, and then they look at this as a function of, for example, radiation dose or eta position. So maybe starting with this top plot, I should point out this is all traditional PNN type silicon, so you have a type inversion of the doping concentration going on. You see for this Atlas plot for one of our barrels, and then for two end cap disks or selections of end cap disk modules, how the full depletion voltage changes as a function of time, so as a function of radiation. And you can see with the black points being the measurements that by far and large the change of the full depletion voltage is very well described by the Hamburg model. And you can also see this nice type inversion point here that till your doping type changes. Your depletion voltage gets lower and lower, and then at some point you change and you get an increasing depletion voltage, and this will keep on going further and further as we move on with run 3. Then maybe this is more detail than I can go through at this time. I could just point out that, as I said, by far and large, we have a good agreement between what the Hamburg model predicts in terms of also leakage current, which is shown here for different parts of Atlas barrels and end cap disks. And you can also see here that there's a continuous increase as we keep on irradiating, and then sometimes a drop when in the shutdown we warm up the detector for a little bit. Then again, moving topic now to new structures. Fast signals is something that has been presented already in some of the talks and in many of the posters and other presentations. Also, one presentation straight after this is low gain avalanche diodes, and I think this has been shown. This is an area of large R&D with a significant number and growing number of manufacturers producing it, and it will be installed both in CMS and in Atlas in the next upgrade. So the basic idea, I think this has been shown, is that you have a thin gain implant here, which gives you extra large electric field, and there is where you have a moderate gain. Two areas of R&D is what I want to highlight here. One area is that in the geometry, you have typically an isolation between the individual pixels or cells from the LGATs, and that is effectively an area without no gain. So you could call it dead area, and that results in a fill factor smaller than 1. There's different R&D areas going on in making designs which have an improved fill factor. For example, one example here is this HD LGAT, where you reduce the dead area with a trench to use the isolation between the individual pixels. There's deep gain layer LGATs, and then there's AC LGATs. They will be presented in the talk following this one. Then yet another area of concern or R&D on LGATs is radiation hardness. I mentioned in the beginning that doping is changing, in particular acceptors are removed, and you can see that the gain layer in LGATs is reduced as you radiate. So here you have an acceptor concentration as a function of radiation dose, and you see the trend is clear that through all these materials acceptors are reduced. This is the same in LGATs, and you can mitigate this radiation-induced performance degradation for a while if you increase the bias voltage, but only up to a certain point. And then to cut it short, current research shows that co-implantation with carbon helps to improve the detector performance here. Then very briefly, another area I want to touch on is the tools that we have to characterize sensors. They have been, for example, used in several presentations this morning already. Transient current technique is a method where a short laser pulse is injected in the silicon, and typically this started with a red laser that you can inject from the top or from the bottom. And if you look at this absorption coefficient as a function of wavelength, this has a very high absorption coefficient, so this red laser is absorbed pretty much at the surface, but gives you a reasonable 2D spatial resolution. If you change to an infrared laser, you get much less absorption, so you can go all the way through the silicon, or you can, in this edge TCD configuration, shine in from the side. And the most recent development here is to go to a laser that on this plot does not have any absorption coefficient, because there you need 2 photons at the same time, meaning within a femtosecond or so, to bridge the band gap. And in this 2-photon absorption process, you actually get a very point-like resolution that allows you to study effects deep into your sensor. So, example here, with this PR plot showing for a single photon absorption mechanism, you have signal all through your detector and only in one point for a TPA system. And just very briefly here, the comparison from one of our PhD students, where you have single photon absorption and 2-photon absorption imaging in a TCT system of an HV CMOS sensor, and this deep N well can only be resolved in the TPA system. Then the last bit I'm going to touch is extreme fluences, where this extreme typically means FCC fluences. Here shown on this first plot are thin 75 micron thin LGATs, and I've crossed this out because there is no gain anymore at these fluences. These are just pad sensors. And they are tested up to 10 to the 17 neutron equivalent here. And there's 2 plots at the bottom to show what they do. So if you look at this plot of trapping as a function of fluence, you can see that trapping, of course, increases as you keep on irradiating, but not as bad as you would have expected from if you extrapolate from lower radiation doses. So that is one part of good news. Then the other part of good news is here in this plot, where as a function of bias voltage, you look at the charge. You see that for sensors for 3 different fluences, the highest one again, 10 to the 17, there is still something like 3,000 electron signal to be collected at this high dose. And then last result plot is from 3D detectors made at CNM, and there, maybe just to summarize here on this, you can see that you still get a reasonable charge for 1 times 10 to the 17 or 3 times 10 to the 17 neutron equivalent. And if you look at this 2D map, you see that quite clearly you can resolve, like in Lena's measurements earlier, the 3D structure of the sensor. These sensors are still alive at 3 times 10 to the 17. That brings me to the end of the talk. So as I said, this was biased and was only able to cover a few highlights. And there's a few other things but I'm not touching here. Maybe more I should say that our original mission has been achieved with silicon for the phase 2 upgrades available, and construction has started. RD50 keeps on to be the one collaboration that works on the radiation hard silicon, also beyond. So if you are now thinking about, for example, the FCC, RD50 will be one of the places where this silicon is developed. And with the results that I've shown you, we are no way there yet to get something like 5 times 10 to the 17 performance. But what we need is, lacking in with Armin's talk at the beginning, above everything, I think more young people to work with us, to help us, and to have fresh, creative ideas. Thank you very much.
Thank you, Uli. So we'll take questions. There is one over there in the middle.
So it seems to me that one of the successes of this activity has been the ability to model the leakage current and the defect and the depletion voltage variation over time, and I think that's a real asset for the LHC projects. But maybe one of the disappointments has been the thing that you alluded to early on about the defect evolution, understanding the fundamental impact of things like carbon and oxygen. And it's clear that in the LGADs, carbon plays an important role. It's not obvious to me how well understood that is or how motivated it is. And I wonder what you think about the prospects of improving our understanding, because it seems to me this would be beneficial in terms of designing future detectors to withstand higher radiation levels.
Jeff, you are clearly right. Yeah, this is one of the points where a lot of activity is going on in characterizing the defects. But I would be a bit pessimistic here and agree with you that RD50 has not achieved there so much. We have identified defects, but for example, in the carbon case, what we were not able to do is tell from first principles, if you use carbon, this will work better. You will have seen a sketch I had earlier on that seems to show why carbon works, but this is nothing specific about carbon. I think you have a good point there, and I really can't argue against that. Sorry.
More questions? Uli? I have actually, yeah.
Hi, thanks for the talk. I was wondering if you could comment to what extent it's perhaps sensible to spend lots of time doing R&D, trying to make things radiation hard to 1E17, when you could just have replacement detectors, as we plan to do in the inner system for Atlas. Given that
you mean like LGATs to replace LGATs? Or?
Well, no, I more meant that you can spend, maybe 80-90% of your time trying to make the detector system radiation hard for the last few years, or you could just build a spare and just change it over. And I just wonder if you could comment on what you think the best use of resources is.
I can give you two parts of an answer there, if I may, fast. One is, I think we were talking about the young people already. I think we need the R&D for PhD students, for master students. We cannot just say we build off-the-shelf phase 2 LHC trackers and then replace them every few years. That's one. And the other is, when I started, and that was on Delphi, then 10 to the 13 seemed like a very high dose, and we were not sure if the silicon would master that. And I think we will, with the time that we have, very easily reach the required 5 times 10 to the 18. I think it's an exciting challenge that we should meet. And maybe last part is, if you go to your funding agency and you want funding for the future, R&D funding, then you better do something that is an improvement rather than building the same tracker again. Maybe it's a bit political, but
that's an interesting question and discussion. I think might be a different point of view. More questions? No, I think it's then time to move on to the next speaker. Thank you again. Where is the mouse? So Jennifer from University of California will discuss about AC LGAD. It's okay? Yeah? Well, you can hold it or...
All right,
Or you prefer this one?
oh, I think, yeah, that's
Okay,
works.
please.
Okay, I'm going to present AC LGADs, and first of all, I already want to acknowledge collaborators from many different institutes with whom we're involved in a variety of projects and activities. As a little introduction, precision timing is very strongly motivated, especially in the upcoming HLLHC, to compensate for the pileup brought on by the very high luminosities, and as well the radiation damage that the detectors are going to sustain over their operation. So for now, still in the phase 2 upgrades of Atlas and CMS, these will be a little bit separated. So the tracking detectors, so based on silicon pixels and strips, are going to be upgraded and improved, as we've heard. And then there will be dedicated timing detectors to provide timestamps. However, in the future, it's quite likely that we want to move towards more truly 4-dimensional tracking and timing detectors instead of having them as separate systems. And one very interesting technology for this are low-gain avalanche diodes, LGADs. As the name says, their main characteristic is a low to moderate gain compared to, for example, SIPMs of the order of 5 or 50, maybe sometimes up to 100, provided by a p-type multiplication layer. And timing resolution of 20 picoseconds, probably a bit less, can be achieved with the sensors up to date. And they've also demonstrated decent radiation hardness up to the order of 10 to the 15. And as a side remark, the neutron equivalent might not always be a suitable unit to describe the gain layer deactivation here. So there are also quite some varieties of LGADs already with all their own prefixes, and one of them are the AC-coupled LGADs. So here below you see a little comparison sketch. So in a traditional LGAD, each segment, pad or pixel has its own gain layer with junction termination extension and a p-stop that end up taking some space, resulting in dead area, and they might also affect the leakage currents or the breakdown behavior of the sensor. So in an AC LGAD, this is all a bit more simplified. So the gain layer, N plus electrode, dielectric, they're all continuous pretty much, makes the lithography masks more simple and provides essentially a fill factor of 1. And so going in more detail, so these are also referred to as resistive silicon detectors, although nowadays resistive silicon detectors don't necessarily need to be AC coupled. Like I said, the layers are continuous already, so the only thing that's patterned essentially are the metal electrodes on top, so there is quite some freedom also for the geometry and size and everything of the electrodes that one can use. And the signal is, or the charges are collected at a resistive N layer, so they're not collected immediately, and the signal is then capacitively coupled over the dielectric as an image charge on the metal pads. And finally, what this results in that we have quite some significant sharing of signal charge over the metal pads, and we can use that to extrapolate for position resolution. Hence, we could have much coarser pads than in a conventional sensor, still providing a good spatial resolution. And this is also advantageous in terms of the readout electronics, so that the channels don't need to be so many in number and not so closely spaced. And some development areas are quite universal to LGAD, so such as the gain layer doping, as we have heard or can see in posters, and to get to even better timing resolution, mainly by reducing the Landau fluctuations. One key trend is also to go down still from a typical 50 microns to 30, 20, and we'll see what we get. And then a bit more specific to the AC LGADs is this resistivity of the N+ layer, so it needs to be resistive but cannot be too lowly doped, otherwise you might end up depleting it. Dielectric thickness, and then finally the already mentioned versatile segmentation of the metal layer, so the readout electrodes. And so I'm going to show a few results from mainly strip sensors produced by BNL and tested at the Fermilab test beam or just in the laboratory with the laser. And mostly we've been looking at different strip pitches, metal widths, and so on, and see how that affects the performance. As a very quick recap on the position reconstruction, so we look at the fraction of the signal that's seen in, for example, here now 2 strip channels, and use that, it's probably not well visible, to calculate the position resolution. And what also affects this is the signal to noise ratio. So again, AC or LGADs in general are quite favorable here due to their internal multiplication. And here we see some results from this BNL strips with different pitch. So here, fraction of the signal on one strip depends naturally on the pitch. And then when we look at the position resolution finally, so yes, the smallest pitch gives the best timing, best position resolution down to less than 5 microns. But actually, when we look just from strip center to strip center, these are actually quite similar. So even a 200 micron pitch strip provides around 15 microns of resolution. That's by a factor of, should be 5 or 6 better than in a conventional readout where you're limited by pitch divided by square root of 12. As for the timing resolution, so I can tell already that with those strip sensors previously, around 28 picoseconds of timing resolution were achieved. So in that sense, AC LGADs are fairly similar to conventional LGADs because you still are mostly relying on the gain layer to provide a fast signal. And the main components here to timing resolution are the Landau fluctuations and the jitter as well. So also here you can use multiple pads for reconstructing the time. But you need to take into account that because the signal is shared, so on a central segment you'll have a large signal, but if you also take the neighboring one, that is already much lower. So the rise time has already increased, and the signal of noise relatively decreased. So you will need to weigh this by the amplitude, if at all. And so this ends up being a bit opposite, essentially, to the position resolution, which is best just between strips. The timing resolution will be best when there's large signal. And so far, so good, but we wanted to look a bit more into the fundamentals of charge sharing. And what we see from the amplitude profiles as a function of position are that they're actually not smooth. So you can really distinguish here in the narrow pitch even localized contributions here from the neighboring strips. So naturally the charge sharing is due to the common N+ layer that connects all the pads, but it's not quite as straightforward that you just have a hit in one segment that then shares the charge with the neighbors, but there is charge directly induced also on the neighboring strips and then fed back. And this also scales with the pitch, for example. So here we can see actually contributions from 2 strips away. When we space the metal further apart, then those are not really visible anymore and are also getting smaller and smaller the wider the pitch gets. And we've also observed that at long distances, we still see some kind of signal component that's well above the noise. And quantified this by having a track on a specific strip and then looking at strips further and further away. So first of all, this does scale to some degree with the distance for all those different strip types that we have investigated. But further away, so after the second neighboring strip on each side, this seems to actually level out. And this is not entirely understood yet, so the TCAD simulations are not able to reproduce this. And it's going to be interesting to investigate this further and see just how much the N+ layer affects this. Something similar can also be done with the laser. So this previous were all test beam results, but we can also work with the laser in the laboratory. These are different individuals now, so newer production AC LGAD strips. Again, we get down to around 10 micrometers of position resolution, but this other sample here, the one in green, behaves quite differently from the others. And that was rather interesting to see because the main difference here is the strip length. So for AC LGAD scales, this is a long strip at 2.5 centimeters. And also when looking at just the amplitude profile, so note that you have cutouts here where the metal covers the sensor, especially for this longer strip, 2 microns. This is the main channel, but you actually see a signal even 4 strips away. And again, once you go beyond the second or maybe third neighboring strip, this looks rather constant away, but is significantly higher than 0 and higher than the noise. So something similar observed in this case. And finally, another interesting point of study is the mentioned shape of the electrode, which can be quite versatile, and how the capacitance of the strip will affect charge sharing and also, well, the capacitance. So one approach here in a recent FBK production is to have very interesting electrode shapes, and one I'm showing here is a strip essentially with metal cut out. As you can see here directly, you can reduce the capacitance of the strip by a factor of 2, roughly. And we are still investigating just on what impact that has, both on the charge sharing and then on the noise of the front end. Briefly, the impact of the N+. So it can be sometimes challenging to compare different vendors, also because this might be proprietary information. Here's a pad sensor from HPK. Red is a lower N+ resistivity, blue is the higher, and the difference in charge sharing and also in the position resolution is quite clear. And finally, going to some near future applications for likely AC LGAD, specifically Pioneer, where I also have a poster about a very recently approved experiment studying pion decays. So here, LGADs are to be used for the active target. So roughly a 2 by 2 square centimeter area. Pitch is envisioned to be around 200 microns. Here the main challenge is the large dynamic range, since we need to be able to detect and separate signals from the stopping pion and the almost MIP muons and electrons. And here, interestingly, we go to the different direction than we have most of the time. So instead of going to a thinner sensor, we actually want a thicker one in order to have just more active sensor volume. And secondly, mentioned yesterday, the Electron Ion Collider, Detector 1, very recently formed just a couple of weeks, 2 months ago. So this will largely be based on the ECHE design, but also from the merged Athena Proto collaboration or consortium. Both designs include a time of flight particle ID detector layer with AC LGADs as the baseline technology, so here in the barrel and in this forward region here. And R&D efforts are considerably ramping up now, also ongoing. And here, as opposed to HLLHC, FCC, many other future colliders, the radiation hardness is much less of an issue, really. So, but here we are more challenged by this combination of really precise timing and spatial resolution in one layer, and also by the requirement of having very low material budget. And so some critical decisions on sensor geometry and fabrication and all are still to be made. So to summarize, thanks to this intrinsic charge sharing by the common and plus layer, AC LGADs can achieve quite remarkable position and timing resolution, and also with much more widely spaced apart electrodes than conventional sensors. This charge sharing is quite a complex phenomenon, actually, and I personally find rather exciting to discover how many different parameters of the sensor interact and affect each other. And in studying these, we can use both test beams and lasers, and also use timing information to study these better, to separate signals from noise. So there are very extensive research efforts on AC LGADs towards precision timing, and then also 4D tracking in general for many future colliders and experiments. And all the research we do now is going to be quite relevant for tuning the sensor properties to their respective application as needed. And also including a very big topic, the development of fast readout electronics. And I believe that those properties like fast timing combination with also fast charge collection time are also going to be rather interesting for other fields than just high energy physics, just photon counting, maybe medical imaging as well. And thank you for your attention.
Thank you for the talk, and time for questions. We have two over there. Maybe we start with Norbert, and then there will be Christoph.
Yeah, thank you very much for the nice presentation. I have a question for slide 5.
Yeah.
I mean, the structure is remembering on the structure of RPCs, resistive plate readout. Now,
Yeah.
why is the bipolarity of the signals, is this due to the capacitive coupling of the electrodes, or
Yes.
why is it? Yeah, okay.
Yes.
And the other question related is, did you measure the decay time, so the amount of time that the charge needs to get from the resistive layer to the output, to the high voltage supply, basically?
No, that we haven't measured directly. We have studied these undershoots occasionally, so they were just the recovery of the signal back to the baseline, but I think those are not the same thing.
No, what I'm after is actually, I mean, like in RPCs, there is some time it takes to get the charge out. Does that probably hinder the rate capability of your device? I mean, the resistive layer, the charge has to be moved away.
Yeah.
And it
Yeah,
takes
so
time. It depends on the resistivity per area and so on.
Exactly. So
Yeah.
there you always end up having a compromise, because as we saw, on one hand, you don't want to have too much charge sharing, but if the N+ layer gets more resistive, first it could deplete, and then it might also delay the charge extraction actually too much.
Okay.
I do not have any quantitative.
Okay, you
Numbers
don't
on
know
this.
what the rate capability could be.
Well, again, we have studied that more just with the signals themselves.
Mm.
So studying
on the long distance charge sharing, so there is an interesting interplay between the resistivity of the N+ layer and the preamp input impedance. And I was wondering whether there were studies on the subject and whether you could play with either of them or both of them.
related again to the signal undershoot, my colleague has compared at least 2 different termination resistances, but we haven't done that anymore on these AC LGADs. We might still do that. And one other factor is just as the strip gets longer, so also the strip resistance itself increases, but on the other hand, the interstrip resistance then decreases, and so on. And these are actually not so trivial to calculate, for example, because you start needing actually 3D simulations that we were perhaps not quite prepared for that.
The question. I have one. Okay, I'll ask this one. What could be the maximum size of these devices? I mean, I understand that there might be a fabrication limit, but is there also a functional limit? I mean, like your N plus resistive thing is a bit related to Norbert questions.
That's one of the main questions, exactly, because we originally thought that there would be only a fabrication limit to the size. And now we are noticing that actually increasing the strip length isn't as direct as one could have thought. So that's the question. It's very much in progress.
So maybe we'll take the last question here.
Yeah, can you go to slide 6, I guess?
Maybe.
Okay, I think it's, no, go one more. There is one with the resolution as a function. Oh, this one, yes, this one. What is the width of the strip?
And the strip width is always 80 microns.
Okay. So it's even in the middle, it's slightly better than the geometrical.
Yeah.
For all of them, okay.
Or let's say the middle is a lot better, and then still in the center of the metal, it's still significantly better.
Okay, I propose we move on. We thank first again Jennifer.
Perfetto.
So we move to Alessandro, and again timing with 3D trench pixel sensors.
So thank you very much. So in this presentation, I'll show you how we achieve this 10 picosecond time resolution with these innovative 3D pixels, which are called trench type. So this is the outline of my talk, but it's just an excuse to show you how the matrix of pixel is done. So this is one of the pixels, and in this particular matrix, the pixels are connected by metal in strips. So we have spoken a lot of challenges in tracking. I will be very fast. I will show you how the design and the new experimental results we are producing these days practically, and then some conclusions and outlook. So we have seen this many times today. The fact that we need time to disentangle the complication of many superimposed collision, but also with many collision, we have to deal with very important radiation damage, and these are two very important things that we have to deal with. So how do we do this in the next years? Atlas and CMS, they are using a single timing layer to start attacking these difficulties. LHCb upgrade 2 in the 30s, we are planning to try to put the time information at the level of the pixel, and this allows to recover the tracking capabilities. And FCC in the future, we still have to go further away from the point of view of time resolution and fluences that we can stand. But one has to remember that the spatial resolution, the time precision, and the radiation hardness are required together at the same time, and this is something important we don't have to forget. So why we have chosen to study 3D sensor? Well, because the short interelectrode drift distance give rise to extremely fast signals, and so this is a way to have okay, yeah, I don't know, it stops from time to time, okay. So this is the way to have fast rising time, so to get very good timing resolution. Also, the fact that with the 3D technology, you can design your electrode shape in the best way you would like to do. And we expect for these detectors an unmatched radiation hardness. It was reported up to exceeding 10 to the 17, 1 MeV neutron equivalent. And the 3D columnar geometry, at least the columnar one, is a production-ready technology nowadays. So let me briefly summarize where the time resolution of 3D sensors come from. This is simplified, but there are few elements that enter the time resolution.
One is the time walk, obviously. One is the jitter due to delta ray. This is the Landau fluctuations, which in 3D, they do not exist because the Landau fluctuations is in the direction perpendicular to the direction where the charge is collected. Then you have non-uniformities due to non-uniformities in the weighting field and in the charge carrier velocities, which is something that depends on your geometry. And then you have the noise of your amplifier. I think that an adequate TDC will make the digital jitter negligible. So at the end, we are left with these two components, which is the non-uniformity of the sensor itself and the electronic noise. And so we have come to such a design where, by using these trenches here, we try to make the weighting field as uniform as possible by design and to work in a velocity saturation regime of the charge carrier in such a way that as much as possible all the signals will be all identical to each other. And then, okay, still we will have this part, which is the noise of the front end. And we do not have gains in these devices, and increasing the sensor thickness sometimes cannot be an option because you have to work with reduced radiation length. So if you look at this solution at the simulation level and you compare it with the traditional columnar one, you see that the weighting field and the velocity map are much different from, let's say, a square columnar 3D design and a trench design. So in the two components, those are much more uniform with respect to this. And this translates into, let's say, more uniform and faster total charge collection time, depending, as a function of if you illuminate this detector in a uniform way all around the active area. So you see this is much larger and much less uniform than this case here. So this looks very interesting on paper, and we have built this. So this is the final choice of our geometry, 55 by 55 micron to be compatible with existing front-end ASICs. We have a trench which is 40 micron large, and it's 135 micron long. It does not extend up to the total thickness of the active part, which is 150 micron. And so this is our pixel, and this is how the matrix look like. This has been produced. We had two production run in 2019 and 2021 at FBK. This is let's say, it's a standard process based on the deep reactive ion etching technique. And so these are one of the wafer that came out from one of our production. We design many devices, single pixel, double pixel, pixels arranged in strips, various type of pixel matrices, and I will show you some result on these devices. So the topic of today is to show you recent beam characterization of 3D trench pixels. So we have those, let's say, various test devices consisting of a single pixel that can be read out, 10 pixels arranged in a strip, or a few strips are arranged all together and connected to the same front-end amplifier. As a front-end electronics, we have a custom-made front-end electronic board, which features a two-stage transimpedance amplifier, which is made of fast silicon germanium BJTs. And this is done to fully exploit the sensor speed that one needs to read out in such a way that, because we need to read out the sensor current. This is not a charge amplifier. This is a transimpedance amplifier, really reading the current, optimized for very fast rising, fast signal, and the output has a very fast rising time of the signal. So we are in this at this moment we are in H8 at SPS, and there is a test ongoing. We have 180 GeV pion beam, 10 to the 6 in intensity, and this is our setup. We have a couple of sensors, a couple of boards with this small sensor I show you, arranged one after the other, and let's say the trigger of the system, the timing, in fact, of the particle is achieved by using two multi-channel plate photomultipliers that together, when we use both information, we can achieve a time stamping resolution of the order of 5 picoseconds or so. So the data acquisition of such a system is a very fast 8 gigahertz bandwidth oscilloscope. And this is, I mean, you cannot see it very much, but there are two signals here. One is the MCP1 and the other MCP2, and these are the two sensors in coincidence crossed by the same particle, one after the other. And in this setup, we have also the possibility of using dry ice to cool one of the detectors to test irradiated detectors. This is the last part of my presentation. This is another picture. One of the sensor is mounted on piezo in order to do a careful alignment of the two very, very tiny structures, because we want to use it in coincidence, and we don't want to trigger on the device under test what we want to trigger on the other one. So the usual old way of doing things, but in a micrometric scale. A brief description of how we do the analysis of the data. So we acquire the data. The amplitude is measured with respect to the baseline on an event-by-event basis. And the timing is evaluated with different methods, all done in software. We have a leading edge algorithm. So this is we have a linear interpolation of the rising edge, and then we trigger usually around 20 millivolts, slightly above the noise. We have what we call the spline, and this will be shown in the previous plots. It's a traditional constant fraction discriminator implemented in software at 35% of the total amplitude. And then we have let's say, 100% constant fraction. We subtract from each waveform a delayed version of itself, delayed by half of the signal rise time. Then we trigger at 50%. So these are the methods we use for timestamping. So let me come to some new plots. So this is the pixel that was illuminated. This is the active pixel. The nearby pixels are not connected to a front end, but are grounded in such a way to have the fields shaped the electric fields shaped in the proper way. And so these are the amplitude measured on this pixel when we have normal incidence of the particle on these detectors. So this is an unbiased trigger. We are not triggering all these signals. And these are the Landau, the amplitude distribution as a function of the voltage you apply on the sensor. And you can see that even though even for low bias voltage, we have, let's say, reasonable Landau that do not change very much depending on the voltage. This is due to the very low voltage that those detectors are able to operate usually. This is a plot on the timing performances. So this is a time distribution with respect to the time reference, the MCPs. And we have an effective time resolution of 11.5 picosecond at 100 volts. And this is the scan of the time resolution as a function of the bias voltage for the different algorithms. But let's look at the black one, which is the one which gives us the best results. The time distribution has a slight tail here, but it's an incredible time resolution for this sensor. We have measured the efficiency because we want to know, those detectors have some dead area in the trenches, are not active areas. So we have aligned a single pixel with a triple strip here, 30 pixels together, and we have triggered on this, and we look at the signals which are here. And so the method to find this efficiency, we just plot the time of the events, and we count how many events we have above a threshold. This is a way to determine the geometrical efficiency without being affected by the noise. And so what we see is that we reach, let's say, 80%, which is perfectly compatible to the active area of our pixel. So this is exactly in agreement. And when we tilt the detector with respect to the beam to achieve, let's say, a non-normal incidence, you see that we go very high, and we are reaching practically an efficiency of 100% for these devices as expected. Okay, so this is usually a tilted operation is the usual way to operate this 3D sensor. We have looked at the timing performance of tilted sensor, and so this is let's focus on this part. We have normal incidence and then increasing angle, and there is a slight indication that it might get better for slightly tilted angles, and the reason. You can see the plot of the time distribution here. So small tail at 0 normal incidence, and then this tail goes underneath the main peak. And this is due to the fact that the time response of the sensor is, let's say, faster in this region of the pixel, But then it gets slower when you have all the charge carrier that we have to make the full crossing, even if they are electrons or holes. And so the faster region is the central part here. And when you tilt the detector, a track will cross all the different areas. So somehow you are doing an average of your pixel response in Z. So, and then this is why it might slightly improve. Let me come to the final part of this presentation, is the very recent results on irradiated sensors. We have irradiated the sensor at the reactor in Ljubljana up to 2.5 10 to the 16 1 MeV neutron equivalent. And this is what one would expect on HCB Vertex detectors in a future upgrade after run 5 on the innermost sensor. The setup is the same one, but we are using dry ice to operate those detectors with a reasonable leakage current. And we are characterized single pixel, triple pixel to measure the efficiency, and so on. So the Landau of the irradiated sensor, this is the Landau of the irradiated sensor, the function of the voltage, and this is the one of non-irradiated pixel. You see that the Landau most probable value moves to the right while increasing high voltage. But what you can see is that at voltage, a bias voltage of the order of 100 volts or so, you are able practically to go back to the performances, amplitude performances of non-irradiated sensor. For what concern the time resolution, also, we have for irradiated sensor at 2.5 10 to the 16, we have an effective time resolution of the order of 11 picosecond. So this is a very excellent time resolution for a detector is irradiated to such high fluencies. And still we see the effect of the increasing tilt in the improvement of the time resolution. The efficiency is practically the irradiated strip supplied 100 volts. Sorry, the irradiated strip and the non-irradiated strip. So the red one is they are practically indistinguishable. Okay, so this is what you can see here. So there is no effect practically. Those detectors are still efficient after this huge fluence. And so I come to my conclusion. I think I've shown you incredible results on the performance of these pixels. They have excellent time resolution, and they have the efficiency you need to operate them in a normal tracking environment. They perform very well up to 2.5 10 to the 16 with slightly increase in bias voltage, but with still maintaining the timing performances. So those 3D devices, they confirm their theoretical excellence performance in timing of this particular geometry of 3D pixel, the trench geometry. One thing that I haven't probably stressed enough is the fact that to profit of such detectors, you need an electronics. Okay, this was, let's say, custom-made electronics, but this is the limiting factor. So the outlook is that we will need we will need an electronics. So I invite you to see the Adriano's poster on this CMOS 28 nanometer ASIC that we are building to read out those detectors. So thank you very much.
Thank you, Alessandro. Take questions starting
Hi,
from the back. Yeah.
thank you for this nice talk, very nice result, outstanding result. I have a question concerning the power consumption of the single channel. Which is the power consumption?
But you mean the electronics?
Yes.
Well, this is a test electronics, so I mean, I do not know. I mean, this is very huge.
Okay.
If you want to consider it from the point, I mean, you cannot have this consumption on an integrated ASIC, obviously. The target of such an electronic will be of the order of a few watt per centimeter square, but this is something we would like. This is, let's say, our target, and it's not the one we are having now.
Okay. What about the capacitance of the single pixel?
Oh, the capacitance of single pixel, I think I have a slide. It's of the order of 100 femtofarad per pixel.
Okay. Thank you.
You're welcome.
Nobody has a question, and there is well, we can take this question, yes.
Hello, it's a very nice presentation, thanks a lot. I have a question about the tilt angles. So you have presented 0 and 10 and 20 degree, right?
Yep.
How does it change along all different angles? And I would assume at some point it will saturate and then it will change back again, right? The distribution.
We
of time
haven't
resonance.
investigated very many angles apart of this range, which is, according to simulation, 20 is probably even too much. I mean, right now, our pixels are all connected to the same front-end channels. When you tilt, you will start entering into charge sharing issues between adjacent pixels. So, but this is something we will have to deal at some point. But this will depend on the electronic capability, because you will have some signal-to-noise ratio to deal with. So right now, our test was done really to show that when you tilt it, you recover all geometrical inefficiencies. So this was the main point. Then the rest depends very much on the electronics.
I see, thanks.
You're welcome.
Okay, we'll get the last question.
Yeah, indeed, very impressive results. Congratulations. Slide 7, please. Okay, you show in your TCAD simulations that the geometry is preferential for the trenched solution, yet I fail to understand what could be better than a perfectly cylindrical geometry. What is the reason? I would expect actually that the cylindrical geometry is the optimum.
The problem of this, well, you can see it here, practically. I mean, this is
No,
not
I
too
can
far
see
from a cylinder.
simulation, but what is the reason?
Well, the reason
minus-
is the fact that the charge deposit, which are, let's say, far away from the central column, they will take longer to be recovered. So the shape will change as a function of the radius you are from the central column. So you need a parallel plate detector to achieve, let's say, uniform response all around your area, your active area. This
Then
part,
it's not the weighting field that does it, it is the acceleration then, right?
well, the weighting field does one thing, but then you have to consider the electric field, the effect of the electric field on the velocity of the charge carrier. So you have both. And so let's say, the winning idea of, let's say, those type of sensors is that the weighting field is uniform as much as possible, obviously, and the velocity operate, I mean, you have the electric field which is so high and everywhere that you operate in as much as possible saturated velocity. So the consequence of this is that the shape of the signal, depending on the position of the impact of a particle in your detector, does not change very much. While this is not true in, let's say, a cylindrical or cylindrical-like design, as you can see it here. You see the charge here, it's much slower, the charge collection time, and it's much spread. Those plots are obtained from uniform illumination of your active area.
So it's the 1/r dependence on the field
Yep.
that kills you
Yep.
compared to a constant field.
Then it depends on what you wanna achieve. Huh? But if you want really to push the limit of such a sensor, reach the 10th of picosecond, you have to have this.
Thank you again, Alessandro.
Thank you.
And we are welcoming Christian Wessel from Bonn, who will discuss the Bell 2 Vertex Detector upgrade with CMOS sensors.
Okay, can you hear me well? Yeah.
Lasers here.
And we will sign you at 8 minutes, 5 minutes.
Yeah. Okay. So welcome. Thanks to the organizers for letting us present our upgrade option here at the conference. Yeah, I'm presenting a CMOS DMAPS upgrade for the Bell 2 detector on behalf of the Bell 2 VTX collaboration. So what is Bell 2? Jerome briefly introduced it yesterday already. So it's an asymmetric plus and minus collider located in Japan, and we are aiming for a target integrated luminosity of 50 inverse autobarn and world setting instantaneous luminosities of 6 times 10 to the 35. To achieve this, we want to use the so-called nanobeam scheme that uses very small beam spot size, as the name already induces. Is in one direction, the beam size will be in the order of tens of micrometers, in the second direction, it will be only in the order of tens of nanometers. And from this we gain high collision rates, but also because of the large final focusing, we get a very large occupancy due to beam-induced backgrounds on the innermost layers, and that dominates to be way more than 95 or 99% on the innermost layers. And coming to these are the vertex detectors. We have the pixel detector in the center at very small radii. These are 2 layers of depth fed technology surrounded by 4 layers of silicon strip detector. And the most important figures are that the pixel detector on depth fed technology has an integration time of 20 microseconds, which is 2 complete beam turns. And with this, and with the detector, we achieve a 10 micrometer impact parameter resolution, while the innermost SVD layer can achieve 8 micrometer spatial resolution and 3 nanoseconds cluster time. And more information on the SVD you can find currently on a poster by Christian Irmler in the neighboring room. So why do we want to upgrade? So as introduced by Jerome, there's a long shutdown in 2026, 2027. To achieve the final luminosity, we need a redesign of the interaction region, and this will likely also change the outer shape of what the pixel and strip detectors can occupy. And this then is also its opportunity to install a new vertex detector. And more information on the overall upgrade program can you find in Jerome's talk on Monday. The motivation for a new vertex detector is that for the innermost PXD layer, we actually expect occupancies of up to 3% due to beam-induced backgrounds. And the PXD is not included in track finding, which you can see here, where I show in red the current Bell 2 detector that achieves 92.5% track finding efficiency. But especially in the low PT region, where the particles do not really enter our main tracking detector, which is our drift chamber, having 2 additional layers for track finding really helps in improving the track finding efficiency. So we gain very much in the low PT region, and also with a smaller pixel pitch and a faster integration time, we can significantly reduce the occupancy in the innermost layers, and we want to use a fully pixelated detector to enable fast pattern recognition. So the VTX concept is what we're using. It's the successor of the VXD. We aim for very low material budget. The innermost layers it would be very cool if we can get down to 0.1 layers. We aim for about 1% radiation length. We plan to use DMAPS pixel sensors of 2 by 3 centimeters of size with a pixel pitch of 40 micrometer squared. It's not yet decided. We are still in the simulation phase, but we also want to have a fast integration time. And just for reference, the TID at the innermost layer is about 10 megarad per year, and we have a neutron equivalent of 5 times 10 to the 13 per square centimeter in a year. So for 5 to 10 times operation, we are close in the region that also the Atlas and CMS detectors see, and the hit rate is very high with 120 megahertz per square centimeter. We want to use 5 straight fully pixelated sensors and have the same sensor type for all detectors instead of 2 different technologies as we are currently using in the SVD. And the 2 innermost layers will be self-supported and air-cooled, and the 3 outer layers will be supported by a carbon fiber structure and water-cooled, and the overall power dissipation will be in the order of 200 milliwatt per square centimeter. And this is a cut rendering and a 2D view of the detector. So yeah, we want to use the TJ monopix or derivatives of it. So it was initially developed for Atlas, but the specifications meet the Bell 2 requirements with up to 5 times 10 to the 15 neutron equivalent per square centimeter. It has a small fill factor and a fast integration time of 25 nanoseconds. We might get along with a slow integration time, but at least this is very much what we need. Then there's a second iteration, which is called Monopix 2, that is currently under test in Bonn and several other places. So you can see a picture of the TJ Monopix here, and some first results with the source here, and the iron spectrum. And we are planning for a test beam in a month from now. And here in the table you can see some specifications of the chips and the expected values for example, the noise, the threshold dispersion, and the minimum in-time threshold. So we will see that after test beams and more testing, hopefully in a couple of months from now. So towards the Bell 2 experiment or the upgrade from the TJ Monopix detector, we want to derive the Obelix chip. We want to have a first fabrication done or submitted at least end of the year, and hopefully also start to getting it back. And then currently we are starting the digital design, and the analog design is still under organization. We want to keep the pixel matrix from TJ Monopix 2, but instead of using 2 by 2 centimeter squared, we want to have 3 centimeter in one direction and 2 centimeter in the second direction. Maybe we increase the pitch to 40 micrometer. Currently it's 33 micrometer to have more robustness against noise and adapt some logic for Bell 2 triggering, and may likely, as I said, we can likely come along with 100 nanosecond integration time, because our trigger rate of the level 1 trigger is only about 30 kilohertz, and we want to limit the data throughput rate to something reasonable. So for the Monopix layout and powering, as I said, we need some additional sensor regulators. So we have some 500 micrometer insensitive gaps here at the side. And if we stitch sensors together, then this adds up to 1 millimeter of insensitive region. Maybe we can reduce this a little. And we also further have to investigate the actual integration time to see whether we can gain in the dissipated power per square centimeter when going from 25 nanoseconds to 100 nanoseconds. So of course, if we can reduce this by 30, 50, maybe even 100 milliwatt per square centimeter, we can gain a lot in terms of material budget needed for cooling and other services. We have a first IVTX demonstrator. So for the innermost 2 layers, it's an all silicon layer. It's one single piece of silicon, and we have then 4 layers of 4 sensors on it. And as I said, it's self-supported. Then we have an additional redistribution layer for data and also for power, and the active area will be thinned down to only 40 micrometer to achieve the 0.1% radiation length overall. And the goals for the demonstrator that we currently have are to evaluate the processing, also with the redistribution layer and the thinning, to do some thermal studies. So for now there are heaters on the sensors to imitate some heat load and check whether we can use indeed air cooling to get rid of the power dissipation. And we also want to check the signal quality and the power delivery over the whole length of the chip. Yeah, some first impressions. So this is first design of the thinned down sensor. So on the edge we have in the order of 420 micrometer thick sensors or silicon, and then in the center it's already thinned down quite a lot, in this case to 90 micrometer. And then we want to place 4 chips on it, and the first letters are characterized, and they have a homogeneous thickness over an area of 10 square centimeters with some outliers, but this is very promising for future. On the transition line, so we started first validations with IZM with a simple geometry to get the layer stack and the attenuation and eye opening, and this will be the output driver of the Obelix chip. So you can see the eye opening here. It looks very nice on the first sight, but again, further investigation is necessary. And then we come to the OVTX. Here we want to have sensors that are glued to a so-called truss, a first version of the truss that was built on carbon fiber structures, as you can see here. In general, the design of the OVTX is evolved from the Alice frame, and it's already in production. And you can see here, for example, a thermal mock-up of the thermal simulation for the water cooling pipes, and in general here a layout of the sensors and the electronics and the support structure. And we are going to start thermoelectric and mechanical tests, because that's a very long truss and a very lightweight truss. And just as a reminder, Bell 2 is in Japan, which is a high earthquake region. So of course this module must not start vibrating under earthquake frequencies. So we have to do careful considerations so that we do not just crash our modules by an earthquake. On the transmission lines, these are then the distribution layers for power and data. They are 35 centimeters long. You can see a test set up here. We are currently having some validation for the signal integrity at the far end and performing bit error rate tests at 160 megahertz. But so far, all the results look very promising. You can see an eye diagram here. And this is a good start to further proceed with additional validation and towards the Obelix chip. So I already conclude. So yeah, the Bell 2 experiment considers a Vertex Detector upgrade in 4, 5, 6 years from now. We are planning to build an all-layer monolithic pixel Vertex Detector, which is more performant and more resilient against backgrounds to reduce the amount of background hits from 99%, 99.9% on the innermost layers to maybe 30, 50% on the innermost layers because of the fast integration time. The target specs in terms of material budget, spatial resolution, and time windows seem reachable with derivatives of TJ monopix. The baseline technology then is the small collection node monolithic sensor. The current chip that we have in Bonn and at other positions like in Mainz, in Vienna or Göttingen are alive and are under test. Yeah, the final chip that we want to have is the Obelix. The submission is planned for end of this year. More tests are planned in the short term, and we are preparing to have a conceptual design report submitted by end of this year. And currently you can also check a poster by Ludovicchio in the neighboring room, and we are searching for more collaborators for the future who are interested in active CMOS chips. And with that, I thank you for your attention.
Thank you, Christian. We'll take questions now. Are there any? Hunger starts to kicking. Gianluca has one.
Gianluca here. Thanks for the very interesting talk, Christian. Can you elaborate a little on this redistribution layer technology, how this is made, where?
I am not so much a module expert, an electrical expert. I hope that somebody, Christian is, or Jerome are.
It's IZM in Berlin who is helping us with that.
Okay.
So basically, if you show up like 2 slides, just again the one before, again before. So as you understood, the idea is to cut out of the wafer directly 4 contiguous sensors, as Christian described. But before that, we send the wafer to IZM, which implants the redistribution layers over redistribution layer, just one, over the 4 contiguous sensor. And then we cut out.
Thank you.
More question to Christian? If not, thanks again, Christian.
Thanks for letting me speak here.
And we'll move to the last presentation of the day by Efrain Rodriguez from Santiago de Compostela. Thank you for accepting to switch with the poster presentation.
Yeah, no problem.
Where are you? You're there. Can you speak so that we check?
Hi.
Yeah. Looks like it works.
Hi.
You got a laser pointer. The floor is yours.
Okay. So my name is Efrain. I'm gonna talk about the silicon Vertex Detector with timing for the upgrade to LHCb. First of all, we are going to talk about the LHCb. The LHCb is a dedicated heavy flavor experiment. We aim to study physics beyond the standard model in the heavy flavor decays. If you want to learn about the physics case of LHCb, you have the whole document here in the CDS. And to achieve this, we are going to follow the increasing luminosity of the LHC to 300 inverse femtobars for round 5. And for this, we need to improve the detector we just installed because it cannot stand this luminosity. The current detector that we just installed is the Velo Grade 1. This is fully equipped in the forward region, and it offers a better study in the close heavy flare decays. It's a silicon tracker situated at 5.1 millimeters from the collision point, and it allows us to discern between primary and secondary vertices. If you want to learn more about this, you can see the Gianluca poster he had this morning. So in the upgrade, we have an increased PIlab and an increase in luminosity. This comes with an increased fluence and readout dates. And we aim to maintain the same resolution that in the Velo Grade 1. For this, we have several challenges like high occupancy, radiation hardness, and material budget. So we do several studies. One of the most important one is the timing. But we have a study also in different layout scenarios that could help us with the material budget. And the sensor and ASIC technologies are very important also to keep with the timing needs. And we are going to talk about the airfoil that is on the material budget and the cooling. Also, the vacuum tank is depending on all of the other parameters. So the importance of timing, since we need to differentiate between secondary and primary vertices, with high luminosity, we see that in each proton bunch, we are going to have like hundreds of primary vertices. So with the current Velo, we are not able to differentiate any vertices, as we can see here. But if we increase the resolution, the global resolution to 20 picoseconds, we are able to distinguish primary or secondary vertices. So it's clear that we need a good temporal resolution in the detector. For this, we have two options. The first one that was proposed was to add dedicated timing planes to the detector at the end of the barrel for the Velo. This, thanks to the distance to the interaction point, we do not need to have much radiation hardness in these detectors, but we at least need 3 segmented layers to have each of them 25 picosecond resolution. And this will add a lot of material to the detector, so it's not great for the material budget. And they will be also very expensive. The other option we have is the full 4D tracking, adding timing to every hit in the Velo. This would require a single hit resolution of 20 picoseconds. Since we have several hits per track, we can combine them to obtain this 20 picosecond resolution we need. And thanks to this single hit timing, we obtain a better pattern recognition and better vertex reconstruction, since we can take away tracks that don't belong to the same vertices. As we see here, the 4D tracking also has better primary vertex efficiency reconstruction than the timing planes. So depending on what we're going to do with the sensors and ASIC, we have 2 layered scenarios. And the most key driving parameter is the distance to the interaction point. And we probably end up in a scenario between the 2 of them. So this would be extreme examples. For the scenario A is to keep the innermost radius as we have right now at 5 millimeters. But this will need to deal with a higher hit rate that probably is 7 times higher than we have right now. And it will be with huge radiation dose. So right now we don't have any detectors that can withstand this radiation dose. The option we are currently talking about is replacement during the technical shutdowns. And the scenario B would be to move the detector at 12.5 millimeters. So to keep the resolution of the detector, it will need to have better hit resolution. So we need to reduce the pixel pitch to 42 micrometers. And being the detector so far away from the interaction point, the material budget is very important. So this requires airfoil development and cooling improvements. So we're going to see the sensors and ASIC requirements. The most important, as we said right now, in different scenarios is the pixel pitch. For the scenario B is 42 or less, and for scenario A is 55 as we have right now. And the matrix size will be depending on this. And also the dose is very important. For the scenario A is the limit that we can have right now, and we will probably need the replacements, as I said. The pixel hit rate is it's very important in the scenario A too. We have calculated a 350 kilohertz pixel hit rate. Sorry, this is a typo here. The time between hits, it will be 3 microseconds. And to keep the pileup of hits less than 1% and have a good resolution, we need a discharge time less than 29 nanoseconds. Also, for the scenario A, the ASIC has to be faster than that right now. We will get a hit rate of 3.8 gigahits per second per ASIC, and we will require a bandwidth of 250 gigabits per second per ASIC. So we are going to talk about the 3 sensor technologies we are currently proposing for this upgrade. The first one will be the planar sensors that we are using right now in upgrade 1. They have a good time in resolution achievable at low thicknesses, but with low thicknesses you get low radiation hardness, and we don't see clear timing goals with maintaining signal-to-noise ratio also. For the 3D sensors, they are good radiation. They have good radiation resistance, and the geometry, I mean, the distance between columns helps with the timing, and the proportion the signal is proportional to the thickness, and they have good resolution, diamond resolution, but we got inefficiencies in the hits through the columns of the sensor. And the third one is the LGATs. They have a thin high field layer with excellent timing performance, and since the gain structure is placed on the sensor, they have good gain at small thicknesses that we will need to have good time resolution, and as we can see, we can achieve the 40 picosecond resolution that we need. But the radiation hardness is more important in this type of sensors, and it will be difficult to have different bias because of the irregular irradiation in this sensor. If you want to learn more about the 3D sensors, I have a poster on them. We are doing studies of the capacities of the sensor. The different ASIC technologies we are currently using is VelopX1. It was developed with the Medivis group, and we are considering using the next generation of this ASIC, the VelopX2. It will be implemented in 28 nanometers technology with 5 to 55 micrometer pixel. And we are also considering the timespot 0 and timespot 1 that they are implemented in 28 nanometers with a 55 micrometer pitch. Now we are going to talk about the material budget. As I said, it's a pretty important subject. We have an RF foil that it's used to guide the beam mirror currents to avoid wake field excitation. And it helps to shield the detector from RF pickup from the beam. Thanks to this, we can also separate the high purity primary LHC from the secondary detector vacuum. And it helps to lower the constraints on material gassing since we are in a secondary vacuum. It's used, right now we have a corrugated foil as we see here, and thanks to this we have better tolerance to the pressure difference. And this also helps to lower the amount of material between the hits of the sensor. So for the next upgrade, depending on the scenario, if we go for a scenario B, we'll need to consider a thinner foil or the complete removal of it, since we are farther away from the interaction point. The material budget is really important. The vacuum tank has to be redesigned. Right now we are using the original one, but if we want to move away from the detector, we need to develop a new vacuum tank. And if we keep the scenario A, the closest one, we need to replace the detector, so the current vacuum tank is not usable. Also, it has to be redesigned depending on the airfoil choice we do. Talking about the cooling, well, Oscar did a very good talk yesterday about this. We really need to keep cooling the system because of the huge radiation dose they get to prevent the thermal runaway. Right now we are cooling on CO2 via silicon microchannels, and for the grade 2 we will need to dissipate more power even. And for this we are considering coolants such as krypton and or alternative solutions such as 3D printed technologies in titanium, for example. So as a summary, we are doing several studies for the installation of the upgrade 2 during the Long Shandong 4. As we said, we are considering 2 scenarios, but we probably end up in an intermediate scenario. one very close to the beam line with a strain radiation and a lot of data transmission, and the other one farther away from the interaction point with less data rate, but we will need a bigger hit resolution. We need precise timing, a global resolution of 20 picoseconds, and for this we are considering 4D tracking better than the timing planes, since they are also offering lower overall cost. We are doing R&D in sensors and electronics with the fast timing sensors. We are really considering the 3D sensors, at least on my side. And we are really aiming to around 30 picosecond sensor resolution. The material budget, as I said, is very important, so we really need to do some airfoil upgrades, maybe the complete removal of it, maybe a single pipe really thin, and there are several studies on this. And the new tank and cooling system must be designed. As we said, Oscar did a very good talk on the cooling system yesterday, and you can see all the options that are considered right now. And thank you all for your attention.
Let's go to question.
If the foil between the primary and secondary vacuum can only sustain such a low pressure, is it good for it all? Why can't you just anyway move to the primary vacuum of the accelerator?
So the problem to going into the primary vacuum would be the outgassing of the detector. Like, you really need to have materials that don't have any outgassing at all. And in this upgrade, if we go to the closest one to the interaction point, we will need to replace the detectors, and this is mostly impossible being in the primary vacuum because you would contaminate the LHC vacuum. If we go to the farthest option, we could do primary vacuum since we don't have to replace the detectors anymore in the round 5.
More questions to Efren? I have one while others are thinking. When would you need to make the choice for the sensors to practically have the time to build this?
That I really don't know. I think it's more dependent on the scenario choice. It's because if we wanna have the option, the farthest away option, we will have probably the 3D sensors, since they could take best the radiation damage. But it's more dependent on the scenario choice. If we go to the closest option, we don't need such radiation hardness because we are going to replace the sensors anyway. So I don't know. The sensors are not really the most important factor in the choice there.
Got it. I still have one question to hold people going for lunch. The irradiation should be quite non-uniform.
Yeah, it's completely non-uniform. It's a problem with LGATs. Since we don't have uniform radiation, the bias has to be also ununiform as the radiation, and it's complicated to develop something like that.
Okay, so it's a complication on the system, but not a showstopper entirely.
Yeah.
Okay, I think we can now close the session and thank all the speakers.
Yeah, just a few words. Clearly, the poster session is continuing, so if people want to go and look at the posters before lunch, there is still some time. And then we reconvene at 3:30 in the afternoon. So have a good time.